Chapter 2, Determinants, Section 2.1, Determinants by Cofactor Expansion. If A is a square matrix, then the minor of entry Aij is denoted by Mij and is defined to be the determinant of the submatrix that remains after the ith row and jth column are deleted from A. The number -1 to the I plus j Mij is denoted by Cij and is called the cofactor of entry Aij. As an example, how about we try to find the minors and the cofactors of entries A11 and A32 for this matrix right over here. So what we'll do is we'll take M11 as our minor for A11. So first I'll write out the determinant of the entire matrix. 3, 1, -4, 2, 5, 6, 1, 4, 8, and then I will delete the entries in the same row and same column as A11. A11 is the entry in the first row and first column, so that's 3. So I'm going to delete all of the entries in the same row and all of the entries in the same column, and I'll end up with these entries remaining, so that'll be my new determinant. 5, 6, 4, 8. So that's just 16. Then in order to get the cofactor, that'll be C11. So that's -1 to the I plus j is 1 plus 1 times M11. And that's just M11 because -1 squared is 1. So that's just 16. The cofactor will always either be plus or minus the minor. Let's get the minor of 32 for A32. So that's the third row and second column, so we're going to be looking over there. So how about we write out the determinant again. So that's 3, 1, -4, 2, 5, 6, 1, 4, 8, and this time we're going to delete everything in the same row as 4 and the same column as that 4 in the bottom. So this is what we have left. So that'll become our new determinant. So it'll be the determinant of 3, -4, 2, and 6. Okay, so 6 times 3 is 18, -4 times 2 is 26. Okay, so that means that if we want to look at the cofactor, that'll be -1 to the 3 plus 2 times M32. So that's, well, -1 to the 5th is -1 M32, so it's -26. By the way, notice that in general, the cofactor is always plus or minus the minor, so it'll always be to either an even or odd power depending on where you are in the matrix. What I mean by that is if you look at the first row and first column, then you're going to square it, so you're going to get something positive. If you look at the first row, second column, then it'll be negative because you're going to have first row, second column be cubed when you add it to the -1 power. So you could just build up a matrix of alternating signs, plus, minus, plus, minus, plus, and so on. And in your next row, you'll start with a minus, and then keep alternating. So you could figure out the cofactors just by remembering the pattern instead of actually computing this every single time with the actual i's and j's. You could just trace along the matrix. Well, trace is a bad word, but you could just point along the matrix until you get to whatever entry you need to look at, and then follow the pattern, go plus, minus, etc., plus, minus, and then you could just read off whatever sign it is and just make your minor that sign, and then you'll get the cofactor. So if your matrix will basically look something like this. So for example, C11, like I said, would just be M11. C21 would just be minus M21. just look at the second row, first column. If you wanted C22, then that would just equal M22, because there's a plus over there. How about we express the determinant of A for a 2 by 2 matrix A in terms of cofactors and entries that all come from the same row or same column of A? So for a 2 by 2, the matrix should be plus, minus, minus, plus for our cofactors. So if I look at C11, that should just be equal to M11, which in this case is just A22, right? Because I'll cross out all of these entries and all of these entries, and this entry will be the only one left, which is second row, second column. So in this case, the minor is just a single entry. If I was going to look at C12, then that would equal minus M12, because there's a minus over there in that second column, first row. So that's minus A21, because if I'm just crossing out everything over here, then this is the only thing I have left, and that's the second row, first column. Similarly, C21 will be minus M21, which is minus A12. C22 is M22, which is just A11. So that means that I could write the determinant of A as the determinant of A11, A12, A21, A22. Remember, I'm going to cross multiply, subtract the other one. So I'll get A11, A22 minus A12, A21. And I can rewrite that now in terms of cofactors, because each cofactor is one of these guys. So I could write it as A11 times C11 plus A12 times C12, just by swapping out A22 for C11 and by swapping out A21 for minus C12. I'll just move the minus to the other side, and then notice the minus will cancel and give me a plus. I could also, if I just swap different entries, I could get A21, C21 plus A22, C22. That means I'm swapping out this guy and this guy. Or I could get A11, C11 plus A21, C21. Or I could get A12, C12 plus A22, C22. Just depends on what I want to swap. If A is an n by n matrix, then regardless of which row or column of A is chosen, the number obtained by multiplying the entries in that row or column by the corresponding cofactors and adding the resulting products is always the same. That's basically what we just saw over here. It doesn't matter which row or column. Notice all of these were the first row, these were the second row, first column, second column. The result is the same. That allows us to make this next definition. If A is an n by n matrix, then the number obtained by multiplying the entries in any row or column of A by the corresponding cofactors and adding the resulting products is called the determinant of A. The sums themselves are called cofactor expansions of A. So now we have a way to compute n by n determinants. Before, we could only do them for 2 by 2 matrices. We're just basically going to generalize this concept over here to bigger matrices and look at this computation over here. How about we do an example? Find the determinant of the matrix given over here by cofactor expansion along the first row. So what we'll do is we'll write out the determinant of A as the determinant of 3, 1, 0, minus 2, minus 4, 3, 5, 4, minus 2 in terms of the cofactors along the first row. So we're going to take 3, 1, and 0. I'll start with 3. I'll cross out all of these entries, and I'll end up with this matrix. So the expansion will be 3, I'll keep it, times this determinant of this matrix. So that's times the determinant minus 4, 3, 4, minus 2. Okay, so for the 3, notice I didn't have to worry about the sign because remember it goes plus, minus, plus, etc. for the cofactors. So I could just, keep the regular 3, but now that I'm dealing with the 1 for my next term, I'm going to have to put a minus. So I'll take minus 1, and let's do this minor now for the cofactor. So I'll cross out these entries. So this is how I'll build my next matrix. Minus 2, 3, 5, minus 2. So I'll take the determinant of that. Minus 2, 3, 5, minus 2. And now I'm almost done with this row. Now I've got this 0 to deal with. Again, cross these guys out. And I'll get plus 0 times, this is what's left, the determinant minus 2, minus 4, 5, 4. Not that it matters anyway because I'm multiplying it by 0, so it's going to disappear pretty soon. But I'll get 3 times minus 4, because when you take minus 4 times 2 and you subtract 4 times 3, you get minus 4, minus 1 times this determinant will be this times this, minus this times this, minus 11, plus 0. It doesn't even matter what this determinant is. And we get minus 1. So that's the determinant of this 3 by 3 matrix. We computed it just using 2 by 2 determinants. How about we let A be the matrix in example 3, and we'll evaluate determinant A by cofactor expansion along the first column of A. So in this case, I should hopefully get the exact same determinant by that theorem. I'll write out 3, 1, 0, minus 2, minus 4, 3, 5, 4, minus 2. And this time I'm going to cofactor along the first column. So I'm going to take 3 again. I'll get the exact same cofactor as before, minus 4, 3, 4, minus 2. And now I will grab this minus 2, but because it goes plus, minus, plus, I have to do minus, minus 2. And let's see, this gets crossed out, so I have 1, 0, 4, minus 2. So 1, 0, 4, minus 2, take the determinant of that, and we'll add that to 5. These guys get crossed out, so 1, 0, minus 4, 3 is the last determinant. 1, 0, minus 4, 3. Okay, so then we'll multiply everything through. We get 3 times minus 4 when we take the first determinant, minus the minus 2 times, minus 2 is this determinant, plus 5 times 3, and it ends up being negative 1, which is the same as our previous result, as expected. It doesn't matter which row or column we choose. Okay, how about we get the determinant of a 4 by 4 matrix? So the determinant of this guy should be, well, let's see. It looks like if we choose our column or row carefully, we can get an easier result over here. Notice in the previous example, we had 3, minus 2, and 5, but before then, we had a 0. So our computation was a lot easier, well, not a lot easier, but somewhat easier, because we didn't even have to compute that determinant. When we did it over here, it wasn't as efficient because we computed an extra determinant that we didn't have to because we chose this, well, we didn't choose, we were told to use this column instead of this row. So it looks like it'll be advantageous for us in terms of our computations if we choose a column with a lot of zeros. Over here, it looks pretty good. But it looks like if we choose this column instead, it's even better. There's 3 zeros. So how about we expand along that column? Let's see. The first one should be minus, then plus, then minus, and then plus. So minus 0 won't matter. So I don't even have to write that. So I'll do plus 1 times the determinant of, let's see, if I'm doing this 1, I have to cross out this and this. So what I have left is the 1, 0, minus 1, 1, 2, minus 2, 1, 0, 1. So I have a 3 by 3 matrix. So that's 1, 0, minus 1, 1, minus 2, 1, 2, 0, 1. And then I would expand along this and this, but those will be 0, so it doesn't matter what other determinants there are. So this is all I have to do is compute this 3 by 3 determinant. Again, let's be clever. We've got a column with 2 zeros in it. So if we expand along this column to get this determinant, we can just get away with just computing one determinant with the minus 2. Again, this is minus, plus, minus. So we'll just have plus minus 2, which is minus 2, times the determinant. Let's see. Cross this out, cross this out. We have 1 minus 1, 2, 1. 1 minus 1, 2, 1. And that should be negative 2 times 1 plus 2 when we cross multiply and subtract. And we get negative 6. Would have been a lot more work if we had chosen a different row or column that didn't have as many zeros in it. How about we find the determinant of a 4 by 4 lower triangular matrix? So what I'll do is I'll write out a general one, A1, 1, and then it's lower triangular, so I'll have zeros above. Then A2, 1, and then A2, 2, and then zeros. A3, 1, A3, 2, A3, 3, 0, and then A4, 1, A4, 2, A4, 3, and A4, 4. Okay, let's get this determinant. Again, let's choose the one with all the zeros in it. Or actually, we have 3 zeros over here also. So it doesn't even matter. I could just choose the first row. So I'll take A1, 1, and I won't have to worry about any of these zeros. It'll be plus for A1, 1. So I'll take the determinant of this guy, because when I cross out all these guys, this is what's left. So that's just the determinant of A2, 2, 0, 0, A3, 2, A3, 3, 0, A4, 2, A4, 3, A4, 4. And again, let's cofactor along that first row. So this will be, well, I'll keep my A1, 1. And I'll cofactor along over here, so I'll get A2, 2. And then this will cross out, and I'll get this. So I'll get A3, 3, 0, A4, 3, A4, 4. And I don't have to worry about anything else because of the zeros in that row. But we could just cofactor again. We'll get A3, 3. This will cross out, and it'll be times A4, 4. Or if you like, A3, 3 times A4, 4 minus 0 times A4, 3. Either way, notice that's just A1, 1, A2, 2, A3, 3, A4, 4. So that leads us to this next theorem. If A is an n by n triangular matrix, upper triangular, lower triangular, or diagonal, then it shouldn't be surprising the determinant is the product of the entries in the main diagonal. You just multiply all of these guys. That's your determinant. So you could say it's just A1, 1, A2, 2, etc., all multiplied all the way through ANN. Let's do another example. How about we evaluate these two determinants? So let's take 3, 1, 4, minus 2. And even though I, love the cofactor method, how about we spice things up by computing this determinant in a different way? what we'll do is we'll do it basically this is the way we did before when we cross multiply, but I'll do it by drawing arrows. I'm going to draw an arrow through the terms I'm going to cross multiply. I go from left to right down, and then from right to left down. So this arrow is going to be my positive 1. This arrow will be my negative 1. So I'll get 3 times minus 2 minus 1 times 4 equals minus 10. And you might say, hey, wait, but you've already been cross multiplying all the time. Well, yeah, but I haven't done it for 3 by 3 yet. So how about I show you what that looks like with the arrows. This would be 1, 2, 3, minus 4, 5, 6, and then 7, minus 8, 9. And what I'll do is, how about I just rewrite it so that it doesn't get obscured when I put the arrows on it. 1, 2, 3, minus 4, 5, 6, 7, minus 8, 9. So notice I can draw this arrow no problem, but it becomes a little bit of a problem when I try to draw this one. It's like too short. It should be hitting something over here that doesn't exist. So what we could do is we can rewrite part of this matrix so that it mirrors on both sides. Well, not exactly mirrors, but it extends to the point where I could put the arrow in. I guess it won't be a perfect mirror. So for what I mean is I'm going to take this 7 and I'm just going to repeat it. I'm just going to keep repeating. I'll take this minus 8 and I'll repeat it so that I can draw an arrow over here, which means I also need to repeat the minus 4 and I need to repeat the 5. I basically start doing my entire matrix over again to fill the missing space. Now I'll be able to draw the rest of my arrows. So I draw 3 going down, and now I'll draw 3 going down to the left. My first one's to the right. So I'll multiply everything along the arrows, but I will add these guys that are going to the right, and I will subtract these guys going to the left. So I'll end up with 45 for my first arrow plus 84 for my second arrow plus 96 minus 105 minus 48 minus 72 for all my left arrows, and that's just 240.